Greetings, 216ers, and welcome back from your spring break. This is Professor Kaufman, and what ensues is an overview video of how to get started on Project 3. The two problems on the project should feel familiar, especially if you finished most of Project 2. They reiterate things that we did there. For instance, the first problem will have you recoding the scale functions, this time not in C, but rather in assembly. And the second problem, Puzzlebin, is much like Puzzlebox in that there is an input.txt file. It's up to you to figure out what inputs are required to earn points, as the inputs will be used in the program to progressively move through some stages. However, this time, Puzzlebin, as the name implies, is a binary only, and so you'll need to do some disassembly in order to see what code is involved with that. Let us take each of those problems in turn, and we'll start as we usually do just by surveying parts of the project specification, which is somewhat shorter than normal here since these are familiar problems, and then go about laying down some code and trying to solve a little bit in terms of the puzzle biddy stuff. All right, so you'll see the normal stuff here, the project manifest, makefile, etc. Problem one involves the scale files over here and some test cases. You'll be writing code, and that will be all in this scale update asm.s handwritten assembly file. That's the only file that is required that you need to add in and create, and we'll lay out an outline for it and put together in a second. Puzzlebin is provided. It is a binary, and so is known to run on most Linux distributions, including on Grace. But if you have trouble running it on your particular flavor of Linux, if you're on a WSL or something like that, let me know. I'm interested in compatibility there. But this is binary by intent. There is no source code there because the exercise is to make use of your skill with the debugger and then assembly tools in order to solve it. Problem one has you recoding three functions from Project 2, or sorry, rather four functions from Project 2. They are the scale from ports, scale display special, scale display weight, and scale update over there. Each of those were relatively short C functions, but will be somewhat longer in assembly. What follows is a long treatise on what you should do in terms of hand coding your assembly. Part of this is advice in terms of skills and techniques that you may wish to use. Part of it is also guidance that if you follow these, you're not likely to be pegged as doing nefarious things, trying to get credit for not actually hand coding your assembly. And that's because it's highly possible to take your Project 2 solution and just generate assembly from it if you know how to invoke GCC, things we talked about in class. The kind of code that GCC produces, though, is even less readable than assembly normally is. And GCC is aware of a number of optimization tricks that it will try to use and generally produce things that most humans would have a hard time understanding. Now, you should feel free to do so and draw inspiration from things that are there, but do write your own code there. And some things that we will be on the lookout in terms of clearly compiler-generated code that will receive 0 credit is that you would annotate your assembly very carefully, that you'd use comments, good label names, not necessarily variable names because all we have is registers, but comments indicating, oh, here, this register holds this variable that's kind of representative of what I did in my C solution. You're not obligated to follow this extremely closely, but if you have a nice tight solution there, then that's a great way to do it. Also, you'll be required to use the division instruction idiv x, where x could be w, q, l, etc., as we've talked about in lecture. The compiler tends to avoid using the division instruction because it's long and expensive, but it's a great way to show that, oh, you're actually hand coding and you know how to use it there. It'll be good practice because in the exam, we'll probably have some kind of coding problem that requires you to do things along those lines. Now, if you are not able to finish Project 2's scale implementation, then meet with staff in office hours or make an appointment with me, and I'll be happy to talk through what your solution looked like, where you struggled. I'll show you my solution, and then we will provide you the digital version of the instructor solution to the scale update.c file. No other parts of the project, but that's the main one. And the scale update.c is a sort of guideposts outline of how you'd write your assembly code. You'd want that to be as tight as possible. That's part of why there were provisions in the project code for that to be short. So if you're in doubt about the quality of your solution, you're like, oh, well, I was kind of bumping against the line limits that were on that, then come see a staff member. You have to do so in person in office hours because it'll be a conversation, not just giveaway. And if you are given such a solution, don't share it with others. Have them come in and be with us as well. Okay, general cautions using assembly and some hints are sort of down here. You want to be very sort of cognizant of the registers, the use of registers for arguments, the use of the $sign to indicate constants rather than bare memory addresses over here. These are all things that we started to touch on in lecture and talked about in labs as you're writing code there. So just be cautious about that stuff. Also, we'll talk in short order this week about the distinction between caller save and callee save registers. And so as you're hand coding your assembly, attempt to make use of this set of registers, and we'll look at the sort of the whatchamacallit, the little register like diagram in a second. If you must use this set of registers, there's an additional cost that you must save and restore those, as whoever called your function is going to expect them to be intact in their test cases that verify this. So just be cognizant of that. And down here is generally that is use the blue registers in this diagram rather than the brown registers are callee save. You can use them, but it'll just take some additional instructions to get there. There are a few other things on here, but I'm going to elide those. You can read them at your leisure, but it's a great idea to sort of survey these as you get under order. One thing you'll need right out of the gate is syntax to access global variables. As we'll discuss this a little bit later in lecture, but to get off the ground on the first function, you'll need to access a global variable and copy some value from it into a register. There's some syntax that's a little bit weird associated with this. We'll talk about it now and maybe round back to it later in the course as well when we talk about, if we have a chance to talk about linking, as there's a rhyme and reason for that. Just bear in mind then that if you have a global variable name, a glob var name, then you'll need to access it as an offset from the instruction pointer, the RIP over here. A little unusual, but you'll get a certain set of errors that I'll demonstrate as we're doing code setup out there shortly. Yeah. Okay, so the basic structure of the code that you're to write is given in this section over here. And so in a moment, we'll copy and paste this into the scale update asm.s file once we're getting sort of set up. We'll have to change some things in here because it won't compile out of the gate. But this also demonstrates a number of useful techniques. For instance, there's that some global var thing again to access global variables. There are already set up labels for each of the functions you need to write, scale from ports, scale display special, scale display weight, etc., as well as a few other things that switch between a text section, which is executable stuff here, a data section, which is data that lays out, and we'll talk about the uses for this in a second, and then back into the text section down here for various things, along with the sort of global symbols that are associated with each of these. For your edification, there's a reiteration here of the intent of each of these functions. It's the same as it was in project 2. And so there's been no changes here except that the line limits constraint has been removed, as you'll expect the assembly functions to be a little bit longer. One thing that we'll need to pay special attention to is accessing the fields of structs in assembly. So in C, you have these handy bits of syntax of like, oh, I've got a pointer to the scale thing. I can use this little arrow operator, and that will access the weight or the mode or the indicators and so forth. And if I had a struct in the stack and sort of an actual struct, a little dot syntax that does the same thing over here. Now, what you'll see if you were to translate that C code down to assembly is that all gone are those bits of syntax, the dot and the arrow and such, and replaced by it are certain things that are done at the assembly level in order to access those fields. For instance, when accessing the mode field of a scale struct, that's the middle field up here, it's beyond the weight over there, and if it's accessed through a pointer, thus the arrow syntax in C, this will actually generate an assembly instruction that looks something like this. Where a 5 is being moved into that mode. It could be sort of scale mode equals 5 or something like that. Let's see. Oh, I think there's a minor gaff here. I'll need to fix the header a little bit because it should be a 3 instead. So the byte offset from where the struct starts is 0 for the weight, 2 for the mode, and 3 for the indicators over here. I'll have to modify that quick. And assembly has no notion of what's there is a field of a struct or something like that, but it does know it's moving some bit of data that's over there. And so you would be populating one of these structs with that data or accessing it by retrieving it from there. You have to know what are the offsets for that. And documentation like this, handy little table, it says if you're accessing it through a pointer, the 0, 2, and 3, where each of these are the size and bytes of those fields, this is the kind of things that you'll need to make use of at the assembly level to access those fields. And likewise, rather than if a struct is packed entirely into a single register, then you'll need to shift the fields of those over in order to access them individually and do some masking. In this case, if I was accessing the mode, but it was packed into a single register, I need to shift right by 16 bits and then mask so that only that lowest byte was present, and that would leave me with just the mode. Now, these two activities and this idea here of accessing fields at this low level in assembly should feel familiar because Lab 6 dealt entirely with this in that coins exercise. And so some of the things that you'll need to do in the project are exactly analogous to the techniques that were used in that lab. In fact, you may wish to refer back to it as you're getting off the ground there. As well, that lab demonstrated the use of the division instruction in the first function, and you'll have to make use of the division function at various times in the project. So be aware of that part. All right, let's get some code on the page. I'm going to come back up here to this outline. Actually, let me duplicate this tab here so that I can grab first the code. I'll copy the web address here. I'm gonna zip over here, let's see, and change into my 216 sync directory. I'll do a wget to download that code and unzip the p3 code.zip. And then change in here. You can see these are the files that are provided, and all that I need to do here is to create this scale update asm file here. So let's copy this thing here. Emacs, I'll create a new file down over here. And then let's see, I need some contents for this. So I'm going to rip out the outline here of code, which is relatively short because it doesn't actually include that much code, just some techniques. Now's a good time to remind that what you're seeing here is nicely syntax highlighted because out of the gates, Emacs has syntax highlighting for x86 assembly and various different syntaxes. If your editor is not highlighting things appropriately, then seek to configure it in such a way as to show at least some color schemes to distinguish like the labels, instructions, possibly register names, etc. If you're using VS Code, then I think there's a link here to a little YouTube video that installs an extension and gets you up and running quickly to edit things in VS Code. So you can do things like block comments and uncomment things, which is super handy in assembly there. Okay, now out of the gate, this is not going to compile right because this move X is not actually an instruction, so I'll comment that out for now. And I also need to return from these functions, so I'm just going to plop down a ret over here. Let's see, down here, I can't remember if these things actually are syntactically correct. They're there to demonstrate techniques that we'll talk about in just a second. And so I'll pop a ret down there, pop a ret down here, and then pop a ret down here. So these are now 3 do nothing functions. They technically will return integers, whatever happens to be in the A family register, EAX, I think, because most of them return ints. But I don't really care right now. What I'm interested in is getting this thing to compile along with the test cases. So I'll try first out of the gate a make over here, and I have a, let's see, some kind of thing here, undefined reference to scale display weight. I think I have maybe a typo someplace here. Scale display. Yeah, okay. So I got a typo in that outline. I got to correct here. This is supposed to be to scale display weight. Rather, we'll talk if we get a chance to talk about linking about why this is necessary. Essentially, these global directives make this label available outside C functions, and that's required for this .o file that's being produced from the assembly file to be added to the executable, because there's some testing code and some main code that calls this function. Lacking this sort of global directive here, or where it was misspelled, or if I just commented out, then this thing is an internal label to this file, but not externally visible, not anyplace else. It's sort of like private in some other contexts, but it's best not to sort of construe those two things because it is different in that respect. Okay, so I'll plop down a weight here. Fire up that terminal once more and give this another go. Okay, I'm making mental notes here to correct several things, a byte offset and a label name that's wrong in the outline. I'll fix that. I think there was a Piazza post about that even. I thought I got it, but I must have missed it there. So, okay, and then of course I can make sort of test code. Sorry, not test, prob1 rather. And this will run 40-ish tests at a half point a pop, and they're all failing. But hey, running tests and failing them is better than not running them at all, because you get 0 credit for code that doesn't compile. So we're on a track now. Let's look at a couple of special techniques in assembly that you'll need to make use of. I guess they're not special, they're just different than what you're associated with there. In the C level, they're slightly less convenient. So for the first function, you'll need to make use of some global variables. And if you're recalling the header file in here, you got things in here like this scale sensor port, the scale tare port, the scale status port, etc. Each of these things are defined in a separate C file, but can be accessed sort of via assembly syntax that are represented over yonder. Oh, shoot, I uncommented the wrong thing here. Let me recomment this part, and we'll work on the first function here. And so we'll focus on this syntax here. If I was going to try to access, for instance, this sensor port, which seems like an infinitely sensible thing to do, this first function is supposed to be accessing global variables and then filling in a scale struct there that's associated with it. One of the first things I might want to do is to grab out the scale sensor port so that I can check various aspects of its value. If it's negative, I know there's an error. If it's too high, I know there's an error, and various other things, but I need to access it somehow. And so I would just take this name here, scale sensor port, plop it down here in place of global variable name. The offset is from the RIP, and I have to pick a destination register. I'll just pick CX here. Now, it's a 16-bit value, so I'd want to use this 2-byte word move here, thus the CX and the move W. That's there. And to that end, I may just want to sort of check this here. So I'll do one other thing, which is to move a 0 into RAX. Actually, no, I'll just do a move L. Okay, no. I got to be a little bit careful here. So this is a small move. I want to first make sure that the CX register is completely zeroed out before I do that small move. So I'm going to move that in there. And then I can move let's see, the ECX value into EAX. Okay, so this sequence here zeroes out the CX family register. It will then copy the global variable into the CX. The zeroing out is useful because move W doesn't change all the bytes in the register, rather only the lowest 2. And if there was garbage in there, then I don't want to make use of that garbage in place else. And then the last thing it does is to copy this CX family register into EAX. That's the register that's used for return values. And that handy, let's see, the register summary diagram, if you forget any of these things, here's RAX, EAX, AX, AL. It populates with return values, so whoever's calling me expects the return value to be there. This one is supposed to return an integer, scale from ports. Is to return that. It's not supposed to return this integer, but at least I'll be able to see my code compiled still. I'm accessing this global variable. It's going to be in the return value for the function, and then I return here so I can actually see it did something. It accessed this global variable and returned it there. Okay, that's not what I want to do eventually, but it's at least something. And so I'll make test prob 1 here, and I get an error straight out of the gate. Cannot be used. Hang on a second. Regarding undefined ECX. Oh, shoot. Okay. So this is a common error, and I'm super glad that it happened right now. So you'll notice here that there's this relocation error here. This is the assembler's attempts after compiling to link things together. It generated a valid assembly code, but this thing, ECX, was unknown. And it was supposed to be there sort of in compilation. Now, looking at this, you're like, oh, that's the register. It's a part of the hardware. It shouldn't be needed. But if you look carefully at the code mistake that I made here, which is up top, let's see. Oh, Yeah, I call this dollar $ECX instead of percent %ECX. Now, what that means is that the compiler is looking around for some global symbol named ECX. Possibly, if you left the dollar sign off, it would also be like a ECX, something like that. And so it's a sort of obtuse error, but it gets to the fact that the assembler is generally meant to sort of intake thing that's very syntactically correct, but is also a little bit liberal. And then it's like, oh, well, you said like, I didn't know about this ECX thing. I didn't know about the scale sensor thing. I assume it's a global variable and you'll provide it later when I'm linking against stuff here. A scale sensor port was provided by this other code. However, ECX wasn't present there. If I plop the percent down, it knows, oh, that's a register. I need to generate a different instruction there. So be cautious of that one and look around for problems. If you see a relocation error like that, it's likely if you got some bit of syntax like percent or inadvertently put a dollar sign in, something like that, something along those lines. Okay, again, all tests failing, but I actually want to look at answers to some of these quick to see if I'm getting the right return value here. And so in my compilation, let's see, the shell was over here, and I'm looking at the scale from ports here. Each of those are there. So I'm going to go into the test results here and just look quick. Here's this one up top. In this one, the scale sensor port, that's the global variable I'm reading, is set to 0, and I'm returning 0. So that could be a coincidence, but it looks all right. The other parts of the test aren't passing, but I don't expect them to. And if I look at the second one here, the scale sensor port is set to 562, and my return value is also 562. So yeah, the code is actually doing something. It's not doing the right thing, but I'm correctly accessing that global variable at least. Now, the next steps along this line would be in the code to access other global variables that are necessary, like the scale status port, to do some comparisons and so forth, determine if I'm an error or not, and then eventually to start accessing the scale struct that is meant to be populated with values there. It's a good idea here to just review quickly. You can see the functions that are right here. The first argument here for scales, scale from ports, it takes an argument, this scale business over here, and that was easy to access in C. You just do a scale arrow thing. Now, if you look at the assembly rendition of this, you'll see there's nothing that has to do with the arguments here. And it can be easy to forget, well, where is this argument scale coming in? Hopefully, your lab has started to educate you about the aspects of this, and we'll talk about it more in lecture. But in our sort of preview of assembly, we talked through some registers are used for special purposes. I mean, they're general purpose register, but they also have side purposes. And so if we turn over here, you can review the different argument registers that are in the notes over here. RDI is the argument, or the register that's used for argument 1 here. And it'll be RDI if it's a pointer, named EDI if it's a register, DI if it's a 16-bit short, etc. And looking back here, the first argument to this function in the C side is it's a pointer to a scale. And so it would probably be a good idea here to plop down this little note. RDI is a pointer to a scale t. And this is the thing that I'm supposed to eventually populate with stuff. Now, for instance, if I wanted to do something like, let's see, populate this mode field here, because I've got a pointer to it, a mode field with a value like 5 is over here. Then I can grab this bit of syntax here, copy it in, and it's moving a single byte because this field is just 1 byte big, moving at offset 2, and I need here the register that's associated with where that scale is stored. We just had that. Oh, it's RDI here, so I'm going to change this to RDI here. Now this will move a 5 to the mode field, and that's, again, not the right answer, but demonstration of a bit of syntax that's useful here. And so I'll do the same thing over here. I'll rerun maybe test 2 in order to see if that has any noticeable effects. I mean, there's a bunch of stuff over here that's like a no good, but that's okay. I haven't done anything yet. And yes, indeed, I've successfully returned 562 and also populated 5 in the mode field. I mean, an obvious thing to do, you only change this to 1 here. That would unequivocally pass this test, but probably fail others because this mode is probably supposed to be conditioned on some things like whether or not I'm, let's see, supposed to display something special or display the weights, etc. There. So those techniques are, again, things that have been demonstrated in the lab and also things that you'll want to make use of in the project now. So start putting them into action. All right, I want to zip down just a little ways here and talk about this middle section as it's relevant to the second and third functions here. It's useful to have a global array of bit strings, bit patterns of various kinds. And so the syntax that's laid out in this middle section changes from a text portion of the assembly to a data portion. And this will generally be considered global variables. However, since they're not labeled as global, they will be only accessible within this assembly file. That doesn't matter at all because no one outside of this file is going to be accessing this stuff anyway. It's handy to plop these things down over here because it spares you the need to create any local arrays within functions in the stack. That's kind of painful in assembly. And so this is the prescribed method that if you wanted to create single integers in either decimal or binary format, you can do so. You can also create arrays of integers. This little .int directive says allocate 4 bytes and populate that with a constant decimal 20 or hexadecimal 0x0014 or 0b110 11110 if you want it stated binary. Likely most of you will make use of this. There's also .short and .char directives. The only thing it really changes is how you would access it later on. I'm laying this out as ints, and the technique that I wanted to bring your attention to is over here. It is to twofold, either to access a global variable, that's over here, but you can see I don't necessarily need the global variable to be outside of the scope of this, and rather I've set up an internal global variable, this myint, and can access it here, again, off the rip. The other technique is to load up the starting address for this array over here, my array. That's done with a leak, a load effective address, which will access the global variable as an offset from RIP, but load the address where this data is stored into RDX. And that enables use of things like, oh, if I wanted to grab out the 1th element of this, then I got to do something like here, like move into an index. Let's see, we'll move Q of $1 into RCX, and then if I wanted to populate a register with the value that's stored here off this thing, I could do the following. This will be the start of the array is stored in RDX. So this will be the start of the array, RDX. The index in the array, which I just said I want it to be 1 right now, but you could calculate this and store it as RCX. And the size of the elements, because they're ints in here, is 4. This would fish out an array element from here by calculating what's the start address, that's here, my array. What's the index? It's 1, but I'll multiply that by 4, so it moves me 4 bytes in and grabs this thing over here. I got to move that into for instance, the EAX register over here. Overwrites this other thing, but didn't really care about that anyway. So this will access that spot, which is, let's see, 16 and 4 in hexadecimal, so that's 20. And we could just, sort of like test that by running in this scale display special the contents of what the return register is at. So whatever this function is returning, because that's going into EAX right over here. Let me grab my shell again and look back and see what's the first display special test. That's number 11. So let me just run number 11 here and see. Let's see, the return value should be, let's see, I don't think I quite got there. So this is return value is something astronomical. So I'm going to look back and just make sure I didn't futz that too bad there. Let's see, display scale update, display scale space special, so leak, and then RDX, and then we've got RCX, and then on there. I definitely messed something up here, so hang on a second, I'm gonna fix it. Okay, I'm just being a yutz. I forgot to save the file. This was a good opportunity to just demonstrate a couple of things. I discovered this by looking at the test outputs, not really understanding why I was getting this extremely weird return value over here. And so firing this up in GDB by taking part of the test results near the top are, this is how to run this specific test case in the debugger. So copying that line down and then running it in the debugger, setting a breakpoint at my scale display special function, and then running. And I see down here as I ran, the code sort of outputted, but then I hit this return statement right away, which is different than what the code would suggest. That had a bunch of other things in here, and then notice finally, oh, I forgot to save. So I imagine now on saving and rerunning, I'll quit out of the debugger here, then we'll have somewhat better results in terms, not passing necessarily, but seeing the correct return value spit back. Yeah, here. So here's a return of 20, which was what the intent is. The end lesson here is just, okay, one, there's a technique then to access local arrays or that are sort of stored in global data within the assembly file, but are then readily accessible and sort of treated as local then. And two, as you run test cases, if you encounter difficulties, you can step through the test case by grabbing this GDB line that's part of the test output over there. And set a breakpoint at your function, walk through it. Generally, this is probably what TAs are going to have you do as you start to encounter problems and want help during office hours. So not a bad technique to have under your belt. Okay, I think that's as much as I want to say about the first problem. It's somewhat difficult because it involves assembly coding, but as long as you are disciplined about keeping track of what's where, following your C code, not lying to yourself and instead running code through the debugger and seeing what's actually happening in it, most folks meet with general success here. The number one bit of feedback that students have, past students to future students, is be very diligent with commenting your code, because all it takes is a day of not attending to it, and most of what's in your mind will be lost. And so you have to rely upon what's on the page to guide you. And if you're looking at just a long stream of assembly instructions without any comments to yourself about what your intent was, then you're likely to encounter a lot of difficulty. So have at it. The second problem is Puzzlebin. And this involves an executable that is present in the code pack. I will just zip over here quick and show you where it is. It's here at Puzzlebin. If you try to open it, you'd see gibberish because it is an x86-64 executable. You can ask about it over here. Let's see, what kind of file is Puzzlebin? It's here. If you're looking for where's the C source code for it, it's in my home directory, but not in yours, because the intent is for you to analyze this thing and try to make sense of what should be in this input.txt to get you some more points, similar to what Puzzlebox is at. Now, don't despair. This isn't a sort of brute forcey effort, because every executable needs to carry with it, these are the actual instructions I'm going to execute. And we'll see in just a moment that the debugger is capable of disassembling that. And there are also tools that can take this executable and reformat it back into approximately the assembly instructions that are present in it. Slightly different format than what is present in the hand-coded assembly, because the disassembly tools follow a somewhat different convention than the assembly tools on that, but I'll digress here. Generally, the structure of this is the same in that there are series of phases. So passing phases by finding the correct inputs to them will earn you points. But just as was the case in Puzzlebox, there's some randomization. So the first thing will change is the user ID to get that thing to plop out right. We'll generally stick to the convention that per phase, each of those is an input line. And the stages get progressively more difficult. If you feel compelled to, you can skip a phase by plopping down the special token skip. That will deduct a point, a minor penalty, and move you forward. It will also not necessarily reflect the state of the random number generator that's used within it. So if you skip, then there's no guarantees that when you return to the phase, your later answers will be correct. So be cautious about doing that. And generally, this will encourage you to get the idea of the structure of a phase, so that if you skip something and come back to it, you can easily resolve the next one because you haven't guessed and checked until you got the right answer. You've rather figured out, oh, this is approximately the way that this phase flows, and I can refigure out what the new answer will be there. So just a few cautions there. Some folks, as they unpack, they get minor problems with permissions. So if you get a permission denied on Puzzlebin, then just change the permissions using a chmod. Sometimes the makefile like sort of takes care of that. Sometimes folks miss. And there's a sort of layout here of how many points per phase. Some more points are awarded later. And if you're counting along, you'll note that, oh, you don't need to solve all of these in order to get full credit. There's a max of, sort of full credit is 40 points, but there is actually a max of 60 around here, including phase 7 and some sundry points scattered around if you can find them in there. And we'll talk a little bit about finding things in that in just a second here. So the general advice about how to go about this is to run this stuff in the debugger. So use GDB for this, and we'll do that presently. First, just a bit here, like, so if I ran Puzzlebin on its own, it would say I need an input file. If I ran it on this provided input.txt, I need to change my directory ID because it's supposed to be 8 characters. I'll go back to my old student ID, which was here, and leave this first input line sort of as is. Maybe get rid of these extra spaces just for sanity's sake. So it's a run, and this is not correct, obviously, but there are a few bits of encouragement here for you. I should mention that the failure messages here that's down here, sometimes they give hints, and so it's a good idea to make use of that. But to get any sense of what's going on, we're going to have to use the debugger for this. For that, I'm going to fire up a normal terminal over here and just pop this up. I use Emacs for lots of things, but it doesn't cooperate particularly well with GDB and TUI mode. So we'll make that use of a standard terminal for that. Just a little bit bigger. There's a GB TUI on Puzzlebin, and if you like, you can over here immediately set the args. Let's see, set args to be input.txt. And generally, as you'd run, you'd find that there are some phases in here. So I could break at like phase, and then they'll list up to 7 of these. So there's a phase 1. That seems like an obvious spot to start. And you can see there's no source available up here because it hasn't been included, and there's no debugging symbols associated with it. So it'd be a good idea to put this in the assembly mode. Now, layout ASM is sort of your last resort. When you have no source code, don't use it when you're hand coding assembly, because layout source would work fine in that. You have assembly source, and it's formatted nicely for consumption. But if there's nothing, all you have is a binary, then this will get you some mileage. It'll show here what GDB derives from the executable itself. Each of these instructions has a unique binary encoding, and so it's not hard to go from the bits that are in the executable that encode that instruction back to a textual representation of them. In addition, when you have an executable like this that's running in memory, you can see, oh, the main starts at this byte address. This is where the actual bits that encode instructions to do in main are present in there. And as I would run this thing, so I need to refresh over here. We'll break at phase 1. That's some more distance into the executable over here. You can see there's reasonably intelligible instructions that are listed over here. The other thing that's extremely handy to have in view is the register file. So if I do a layout regis, this will show some of the registers. I'm going to decrease the font size a little bit so I can see all 16 of the general purpose registers. I don't think I'll need any of the special purpose ones. And you can see this window up here, it sort of changes sizes based on font size here. So if I increase it, I only see the original 8 registers that were part of the x86. I guess I don't even see that many over here. So let me sort of keep that in view. This first instruction is going to adjust the stack pointer here, RSP. And if I do a step instruction, then you'll see it changes. It went down by 8 here, and that's something that we'll talk about later on in class about why one needs to do that. It's either to create space in the stack for local variables or to set up a function call, and that makes sense because the very next line here is going to be a function call. So step I will step single instructions, but it will also step into functions. And generally, there might be a few cases where you want to step into the assembly functions that are, all present in this file. However, next line does exactly what it says. It will access a line from the input file, input.txt, and then populate it someplace over here. So if I do a next instruction, I don't want to sort of step into this. Rather, I just want to move ahead over it and get the return value. Then that's, I think, more ideal. So you can see some registers changed. And importantly, if you remember, return values come in the A family register, RAX. That one actually changed, which sort of makes sense. And the RAX value here is rather high, might be a memory address. And it's being copied over someplace. So obviously something's happening there but with it. Copied into RDI. RDI is also a little suspicious because if you're keeping track on that set of registers here, RDI is the first function argument. And if you're setting up a function call of some kind, then that's a sort of logical thing to do, is to populate RDI with something. So let me go another next instruction. And I should say NI is an abbreviation for that. We'll move one instruction forwards. And as well, if you did a next instruction here and just press enter, it'll do another next instruction. Now, I want to pause at this point because two registers, RDI and RSI, have been populated and a function is about to be called. It's prefaced with strcomp. And there are some tricky things in Puzzlebin, but this isn't one of them, that this is really going to do a string comparison. What two strings is it going to compare? Well, there's an RDI and RSI that are set up, and those are arguments 1 here and argument 2 here. So it seems, sensible that these two would be the two strings that are being compared. I might want to know what those strings are. You can even see here that this access here, which is an offset from the RIP with some sort of a constant here, GDB knows, that's where something called quote is stored, a global variable of sorts. And so that's not a bad thing to sort of inspect as well. So I've got these memory addresses in RSI and RDI. They're of interest here. And I just might want to see what's at that memory there. There's a handy examine command that will take a register name like RSI and say, examine what's in memory at that spot. So let's examine what, let's see, RDI is, for instance. And you'll see over here, it's printed out in hexadecimal formats. But this is sort of handy to know that GDB also knows, that particular memory address, it's fairly close to where this inputs value is at. Now, X, like several other printing commands, can print things out in different formats with a little slash here to say print it out in decimal, it's this value. But it also understands, how to print out string stuff. And this part is handy. It's like, how now, brown cow? That should be familiar because it's the default string over here that's in the input.txt file. We can try the same trick over here and note the little $sign. GDB writers also weren't involved in assemblers, and so there's slightly different syntax here of the $ to access registers. If we print out RSI, then you'll see over here, the world's hero, it needs a professional. This as a quote, because it was loaded from this quote over here, is not a bad one to maybe try out here. Now, on my particular terminal, I can't copy and paste this thing, which is slightly vexing. So I'm going to use one little trick that's maybe not, it's something that is modestly useful if you need to copy and paste from here. There's something about like the way that GDB in TUI mode sets this up where you can't copy and paste stuff as well. But if you disable the TUI, and then you can use like your up arrow to find that stuff. Just put you back in normal terminal mode where you can see now I can highlight some stuff here. And in my terminal, if I press Control-Shift-C, I can copy things. Your mileage may vary. I'm going to paste that in over here and save this thing. I may as well just run it over here in my other terminal to see how this thing comes out. And you can see, hey, we got some points out of this here. That phase 1 was passed over here. If I rerun, let's see, I'll enable the TUI here. If I rerun this thing from the start, and I should say, right now, the string that's been loaded is that how now brown cow stuff. So I did a next instruction here. You see EAX comes back as this thing. And there's a test here that's going to happen, and jump not equal down here, which is going to quickly result in this failure over here. So if I do this and then this, then I'll see the little failure message over here. However, now that I have the right quote in, if I were to rerun this thing again from the beginning and just do some nexting here to zip through, this is the string comparison. Let me examine what's in RSI now and what's in RDI now. There should be the same string. If I do a next instruction on this call, you can see the return value back from strcomp here is 0. And that follows the same convention that is used in the basic strcomp, that's part of the C library, where a 0 is returned when two things are equal. You can see the test instruction here will test EAX against itself, and will then fall into this return, which is what gets me points. Now, at this stage, I'm basically done with phase 1. And so I might sort of look at my breakpoints and see this breakpoint 1 here. I don't need it anymore. I could delete it. I could disable it. So I think the disable 1 will disable that. And so if I ask about breakpoints now, then this one is enabled no. So when I would run it, I wouldn't hit it. Only break at phase 02. And give this a run from the beginning here. And you'll see here, now I'm in phase 2 and have a new set of problems to make use of. Some of these things that you can ignore, for instance, like the setup over here, the zeroing out of things, basically everything up to the new next line here. I don't have a next line in the file, and so should probably sort of populate something in there. But in a lot of cases, it's going to be good to try to figure out what kind of format is needed for this line. We can scan ahead just a little bit here and sort of poke around and see, oh, there's use of an scanf function here. This is like normal scanf, except it reads from strings. And like normal scanf, it will need to populate, sort of look for the format that's requested in some sort of a string constant. And so it's a very good idea in the next phase to poke around these strings over here and see what are each of these things, where are they coming from, and see if they reveal anything about the kind of format that I need to plop down here. Is it numbers or another string like hello, or a whole line, hello world, this sucks, something along those lines. So be careful and look as this scanf is about to be called, because there are a bunch of things in the arguments that can reveal what kind of a format is needed for it. Okay, I think that's about all I'd want to say about GDB usage on this. There's one other trick that's extremely useful in this endeavor that is mentioned a couple places in the course, but I'll reiterate it here. This binary file that's in Puzzlebin, you get a sort of narrow window here in GDB that's in the middle panel here of what's involved, but it doesn't really give you any sort of global sense of how much there is, or if you want to search around to find things or things like that. And so one extremely useful tactic is, let's just disassemble the whole thing and plop that down in some file. There's a handy dandy object dump utility that will handle the binary file format that Puzzlebin is in and allow you to disassemble it. That's what the -D option is. Now, normally this stuff prints out to the screen, so if I ran this now, you'd see just loads and loads of stuff over here. Rather, I'm going to dump that through redirection, a technique that we'll talk about later in the class, into this puzzlebin.s file. It'll take just a second because it's a rather long file. And if you look over here, it's 8.7 megabytes, which is, it's only just under a megabyte for the binary version of it. So it's some 8.5 times bigger than that. So let's have a look at this thing, and you'll see output from which was sort of printing out on the screen, but is now plopped down over here in the sort of .s file, this puzzlebin.s. So if I look around for main, there'll probably be a few different things in there, but here's main as a label, and you see these are the exact same instructions that we saw when we sort of started up the program. You can also search for like phase 01. You can see there's a call to it of sorts over here, but the actual code that we worked on is here. The bytes over here are the binary encoding of each of these instructions. They are not what was, this part wasn't displayed in the output that GDB had, just this part was, but it's sort of handy to see this stuff. And if you want a sort of another sort of broader picture, you can scroll this thing through this thing and find phases of various kinds over here. And this is handy to have if you wanted to, for instance, make a note like, oh, in this phase, I think there's some kind of a loop going on. So like maybe I could just to notate here, it's like beginning of a loop, jump out of loop here, things like that. So making some notes like that can be a handy thing as you're trying to figure out what's going on in the structure here. Each of these phases was generated from a C file, and so it's not a bad idea to spend some effort trying to figure out what exactly is the essence of what's happening in the phase here at a C level, to sort of try and figure out, oh, there's a loop and a condition here. What condition? This thing looks like a number. I'm doing some oddness and some evenness and so forth here. So to that end, do your best as you can to sort of reason at a higher level, as that will inevitably fast forward you somewhat towards what you need to have sort of to solve the phase there. Don't be afraid to sort of skip forwards in phases somewhat too, to like, okay, I'm just going to skip to the scanf here and sort of figure out what I need, or skip ahead and see how are these numbers changing over several different instructions. But there's also no substitute for sort of grinding and sort of trying to reason about here's little bits and pieces and let me try to push them together into a higher level understanding. All right, that's as much as I have to say about the project. It is among the most difficult things that we'll do in the semester. So if you struggle, that's just strength being accumulated in your mental capacities. I wish you all luck, happy hacking, and I plan to see a lot of you in office hours relatively shortly. Cheers.